Now, what were we talking about? We're talking about energy distribution in porous media. Now, last lecture I kind of viewed it myself. It went kind of little mathy. So if you don't fully understand the stuff, don't worry about it. We're not going to use too much of that information. The idea of last lecture was to kind of give you guys some background on how things relate to each other. Where does Bernoulli equation come from? How head pressure and everything are relating to each other. The take-home message of last lecture should be how do we define what we call groundwater head actually, our total head. That's the main thing, and the total head has three components: the elevation component, pressure component, and velocity component. And the velocity component is negligible in groundwater because usually groundwater is a laminar flow system, so there is very little inertia in the system. So with that, all you need to know is basically total head is P by gamma plus Z, where gamma is rho times G. Okay, and the key thing we looked at is basically a water column. So if you have a land surface and there is rock here, and if you have water table, okay, you should know exactly how these components are distributed. Okay. Now if I choose my datum here at z equal to 0, I know P equal to 0 here, Z equal to 0, so the total head should be 0. And this is hydrostatics, so the total head should be 0 everywhere, which means my pressure becomes positive as I go down. This is my pressure, P by gamma. And as I go up, it's going to be negative in the unsat zone, this unsat, sat. Okay? And my elevation head, since it's 0, as I go down, it becomes negative. Go up, it becomes positive. Okay? So that is a basic way how total head is distributed in a soil, in a sand column. Okay? Now, well, before we do that, now what happens if I mean, Z, how do I choose Z equal to 0? Datum. How do I do a benchmark? It's arbitrary, really. There is nothing tells me that I have to choose Z equal to 0 here. I can move Z wherever I want, really. Okay. So now, if I move Z equal to 0 here, actually take that as a homework, not as a homework. I just draw yourself and convince yourself. If you have questions, we can talk about in the next class. What happens if Z equal to 0 here? How does this pressure distribution diagram will change? Remember, if Z equal to 0 here, then P equal to, we got to put some numbers here. Let's say this is 5 meter. And this is 10 meter. Okay. Now, if Z equal to 0 here, what is the pressure here? P by gamma. Positive. What is the number? What would be the pressure at this point? Or pressure head at this point, this component of that. 5 meters or 5,000. Oh, okay. Right? 5 meters basically. Because P equal to 0 here, and you're under 5 meters of head, so P by gamma should be 5 meters. Okay. Now, would that change if I moved my datum? Would it change or not?
Would the value change?
Would the value of the pressure over here, would it change if I move my datum around? No. Would it change? Think about that. Like this deep horizon oil well, right? They say it's at a tremendous pressure. My datum is arbitrary. So surveyor said, well, I'm going to move my datum from sea level to somewhere else. Do you think the pressure cannot change? Pressure is a constant. Okay, it's basically, so datum is a completely arbitrary thing. Okay, so from that sense, total head is kind of an arbitrary thing. It's a function of how we choose your datum. So for convenience, we use benchmarks like sea level and everything. So when we talk about total head, it's actually reference to some datum, some fixed point. Okay, and that's kind of my message. So what I would like you to do is, so we chose this as a datum. This is how pressure is, and the elevations are distributed. if I chose z equal to 0 here, I want you to draw this picture, how pressure and the elevation will be distributed. Okay? So think about it. If you have questions, we can talk about it in the next class. Okay? So that kind of concludes how the energy is distributed. Now, why are we worried about energy? Because we are eventually interested in groundwater flows, not in the static system. And the groundwater flow will happen from higher energy, which is basically higher elevation head to a lower elevation head. Okay? So that's the next topic, actually, a flow of groundwater. Okay? We're going to discuss about the groundwater flow problem and how does it flow and why it's doing certain way. Okay? So now there are some basics to be kept in mind. The first thing is water total head, not higher pressure head. Water does not move from high pressure to low pressure. That's a wrong statement, actually. Okay? It goes from higher total head to the lower head. And we're going to indicate head as this big H. Okay? And head is always P by gamma plus C, the pressure component and the elevation component. Okay? Remember, all the complicated thing we did last time, if I take a parcel of water, I lift it up, I created a head. Okay? And then I pressurized that control volume, I created more head, actually. So it's a function of both. Okay? So with that in mind, let me draw a few pictures. Let's say I have a lab where I got this is my lab floor. Okay? I got a soil column. And there is an outlet. Okay. Now the water level here is this much. The water level here is this much. And I will put some numbers. Okay. Now, by definition, the components are, if I want to find head at this point, at the inlet of the column, I need to know the elevation head. So I'm going to call this as Z1, which is and this is the datum. I'm going to decide this as my datum, Z equals 0. So that's my elevation head at this point. And the pressure head at this point will be HP1, this height. Okay. Now, how do I compute that? Well, if I have a pressure gauge, I can actually measure the pressure and in Newton per meter squared and divide it by the gamma. That will give me my head. Or I can just measure that. That is my pressure head, that height, which is in that unit. Okay. So the gauge will measure Newton per meter squared, the pressure, absolute pressure at that point, and then you have to divide by gamma to get the equivalent head. Okay. At this point, it will be Z2, which is the elevation head, and the pressure head will be, let's say, HP2. Okay. So what is the head at the first point? What is the total head? H1 equal to what? It should be nothing but Z1 plus HP1, right? And total head at this point will be H2 is equal to Z2 plus HP2. Okay, so those are definitions. Okay, so let's consider a column like this. Now, if I want to know, so I did this experiment. I got all these numbers. I got H1, HP1, Z2, HP2, and all this stuff. Okay. Now then I remove this column, so you can't actually see this column. I pretend as if you can't see that column. Now, if I ask a question, let's say A, B are the 2 points, inlet and exit of the column. If I released a little tracer here, a blue dye, if I have this information, how do I know whether it will move this way or that way? Just by looking at the numbers, how do I know? water will move from, so bigger H to smaller h. If H1 is higher, it's nothing to do with HP1, it's nothing to do with Z1, the components have no meaning. I got to eventually look at H1, right? And if H1 is higher, it's going to move this way. If H2 is higher, it's going to move this way. Okay? And that's a very important concept. Okay? So let me expand that. What if I took this column now, and I'm going to tilt it? So the gravity is kind of acting this way. And now I got the same cube. It's no more straight. And now I put, it's the same day, the same lab. So Z equal to 0. Okay. Now the water level, let's assume, is somewhere here. Just arbitrarily, water level somewhere here. Okay. So this is my Z1. Z2, okay. Actually, not my Z2. Z2 will be this point. Okay. And then you can HP1, HP2. Okay. Now, if I ran an experiment in this water column, okay, and this is my AB point. Okay. If I did an experiment and put a little die inside the column, remember the thing is sloping this way, right? If I did that, which direction the water will flow, Richard? Go to B to A. Okay. Fine. Right to left, it will go this way. Right to left. Okay, my right to left. Okay, this way. Any other answer? Remember, it's which direction it will go? This way or this way? This way? This way? Pick one. This way? This way. This is 1, 2. To this way. Arthur? Okay. Anybody for 1? You sure? Remember, the majority doesn't win in this class. They got a pretty bad track record. You want to try? Which way? 2? So the majority seems to be 2. Any other answer? You're thinking, Amanda.
I say
2. 2. Go with the majority. Safe bet. Anybody? Any minority? 2. Okay, good answer. Actually, in this case, majority did win because it really doesn't matter. Nobody cares. It's all pressurized system, so it doesn't matter. The pipe could be laid this way, any way you want. Eventually, it's the total head which is going to drive the whole problem. Okay, so you got to really calculate the total head and then deal with it. That's it. Okay, so because that's what eventually matters. Okay, so another trick question textbooks uses, it could be, now the column could be this way, tilted this way. Okay. How many of you are taking soil physics in this class? Anybody here taking 1, 2? Okay. Of course. Okay. Has he started talking about Darcys Law? No, not yet. Okay. What have you guys done so far? Solid, okay, porosity, phase diagram basically, okay. Okay, so the thing can be tilted this way again, let's say. Now if I release it, which direction it will go? In this case, remember it went against the slope, happened to, what direction it will go? Want to guess? This is A, B. Will it go this way or this way? B to A? B to A. Anybody? A to B? Okay. Again, it's the same idea. Forget about the orientation of the column, right? It's always the total head. So basically, you measure the total head, measure the total head. Okay. So how is the head measured? Well, you create a datum. Head is nothing but the water level above the datum. Okay. And the datum doesn't matter. I can create a datum here. It'll still work out fine because it's a uniform benchmark. Okay? So groundwater flow is always dictated by the head level, water level, okay, which is measured from a fixed benchmark or a datum. Okay, so let's do a small problem here. Actually, we'll do it later. Okay. So that's kind of reinforces the flow direction. So we kind of established which direction the flow will go. Okay. The next question is how fast it will go, right? So we solved the direction problem. We not solved this marker problem, which is persistent. Okay. Direction problem. The next question is amount of flow. Okay. So the intuitively what we are trying to ask is, well, now I know the direction. So let me set up a little experiment. I'll make it simple. Let's keep the column straight. Okay. And if I have a head here and a head here, so nothing tricky. Okay. It's all, that's my benchmark. Okay. So the head here is higher than this head, so the flow is going to be this way. So we established the direction. Okay. Now the question is, what will be the flow? What is Q? How much Q can flow through the system? Okay. Now let's think about it a little bit intuitively. If the minute we talk about Q, we should be, which is also directly related to some other property. What else do you think it will be related to of a flow property? Velocity, right? Because if I knew, so well, think of this as an open column. I mean, open tube. If I know the velocity, I know the flow through the system, which is nothing but the continuity would say Q is equal to A times V, okay? And that would still apply here, okay? What would be different between a pipe? So let's say I gave you a velocity. Let's say the groundwater is flowing with a velocity of, I don't know, 2 meters per day, okay? And if, how do I calculate A if it's a porous media filled column? What is A? Let's say the pipe cross section is, I don't know, 1 meter square. Okay, can I use that?
You need to calculate the porosity.
I have to account for the porosity, remember, because in the open pipe, it's 100% void. Okay, in porous media, what is the void space typically? What's the magic number? 40%, right? So if it is 1 meter square, it's about 0.4 meters square. Guess would be without knowing too much information, right? So if I knew the velocity, I can actually calculate flow by just simply doing AV, and the area I got to account for this presence of these solid particle as opposed to the so there will be solids here, right? So the void spaces will be only 40% because of the porosity issues. Okay, so I can calculate that. Okay, but the question is, it's kind of a chicken and egg story. How do I calculate velocity? Well, if you know Q, you can calculate velocity. Okay, or if you know V, so they're kind of interlinked. We'll talk about it. How do we calculate all this? But the bottom line is the fundamental properties I need to calculate Q. Okay. Now let's think about it intuitively. If I force a certain gradient, this is called gradient. Okay, so this is H1. So how do I define gradient? Gradient is, well, we'll talk about it. Basically, if this is H1, okay, which includes the pressure head and the elevation head. If this is H2, and this whole distance is, let's say, delta x, okay, or L. Okay, gradient is head gradient. Is equal to delta H divided by delta x, which is equal to H2 minus H1 divided by L. Okay, so that's kind of a measure of how the gradient, basically it's a slope of this groundwater headline. Okay, so if I draw this line, this tells the slope of this line. Okay, so for a given gradient, let's say I fix this. Okay, what do you think Q will be a function of? Would Q depend on anything else other than the gradient? Stephen. Okay, think of anything it'll depend on? Arthur?
Like neglecting friction and stuff?
No, friction, everything is, obviously it's a groundwater system. It's a pretty low flow laminar system. There's plenty of friction. If I did a column experiment like this, right? I set up well, you guys did it in geotech, right? I mean, in your geotech experiment, you probably did it vertically. Did you do it vertically or horizontally? That's a little thing, okay? Whatever way you can put it, okay? Because that tells me it doesn't matter. It's all about head, right? If I did this experiment, the amount of flow would depend on what for a given column experiment. Let me put it other way around. Yeah.
The amount of time?
Yeah, the total flow will be, this is flow rate, sorry, it should be rate. Q is cubic meter per time, flow rate. Would be a function of what? Still getting used to names here. Thomas.
Yes.
What would be a function of? Anything else you can think of? Okay. Okay, let me put it the other way around. What if I fill this with sand opposed to clay? Where do you think the water will move? More water will move. First of all, between sand and clay, is there a porosity difference? Actually, clay has got slightly higher porosity, right?
Q will be less.
Q will be less for clay. It's got a higher porosity. Okay, it's roughly 0.5 porosity wise because of its plating structure. So if I filled with clay as opposed to sand, Q will be, which one will have more Q? Arthur?
One with more pores.
One with more pores. Clay will have more this thing. Okay, you fell into my trap, Stephen. I'm going to take this column. Okay, it's very simple, right? I'm going to take this column, create just think of actually doing an experiment, right? I'm going to force a gradient. I'm going to keep the water level here, and fill this material, this column with clay, same height, and measure the flow rate. Okay, and then I'm going to empty this thing, take it again, pack it with sand, put the same gradient, measure the flow rate. Okay, which one will be higher, Q in clay or Q in sand? And I also know the porosity of the clay is higher, slightly higher, about 0.5, as opposed to sand. Which one will be higher? You got to pick one. Clay will be higher. Thomas. Sand will be higher. Okay, I like that. Okay. Now there is no majority here, so let's take some votes here. This is tough now. Okay, so we got a sand, clay. Okay. So we got 2 votes each. Now it's tough. Amanda.
Clay.
Hey, Clay's getting a winner. Which one? Sand? Sand. Ooh, sand is beating.
Sand.
Goodness. Okay. Sand has got a lower porosity. Oh, goodness. Okay.
Sand.
Oh, goodness. Okay. You know, it is a everybody jumping. A majority does not win all the time. Clay. Good. Okay. And Thomas, did you pick? What was your pick? Clay. Sand. Okay. You already picked. Okay. Okay. Majority wins again. Majority wins again. Okay. So the trick here, I mean, the trick I threw in, well, intuitively. First of all, forget about, in this case, actually intuition works as opposed to the porosity. If I packed something with clay, you go to your backyard and you got a clay soil and pour some water, okay? And then you go to beach, okay? And hopefully the oil is gone and pour some water. Where do you think the water will soak faster? Of course, sand, right? But actually, the clay has got slightly higher porosity. Okay, so the first message I want to communicate is porosity has nothing to do with the flow rate. Okay, it tells how much space is there, but that doesn't mean that is really completely. It's got some minor connection. Later on, we'll talk about it. But in general, they are independent properties. Okay, just like we proved ourselves, porosity is not a function of grain size. Right? Intuitively, we might thought it's a function of grain size, but it's not actually. Or it's got some mild correlation eventually, but in general, it's not a function of grain size. Okay, so it's the same idea here. Okay, Steven, you seem to be confused. You don't buy into it?
No, I do. It's just the when you compare them, the area, you know, would the velocity just go down? The velocity would be the term that would go down.
Yeah. You got a point there. Area will be different, slightly different. I agree. Yeah. Yeah. We'll talk about it. Why those details we'll get into it. You are right. The area becomes slightly different. But remember, the difference is not much. It's about 0.5 to 0.4. It's not a huge difference. Whereas I mean, intuitively you know it, right? You go to the backyard and pour some water in clay. Okay, and this thing. I mean, in fact, that experiment is the same experiment. What are you doing there? So you've got your backyard, right? Your backyard has got some clay. Okay, and this is my nice beach without oil, of course. When I pour some water, essentially I'm creating a head here. Let's assume the whole thing is quickly saturated and somehow it kind of drains somewhere else. I mean, let's say it's a pot. I mean, let's think of a flower pot, if you will. Instead of backyard, let's think of a pot. A pot filled with sand opposed to clay. Okay. Now, if it is draining away, then this is P equal to 0. Okay. And if I pick this as my datum, okay, then this H1 is equal to 0. And H2 is this height. Oh, actually this height. Okay, and this is P equal to 0, so Z equal to 0. This is my H1. Let's assume it's H1. And the P by gamma is this height. So if I pick this as datum, P by gamma is nothing but my head, right? So if I force equal head, it will flow, obviously we know. The sand part is going to drain much faster, okay? Which means you got to pour more water into the system. You got to keep the hose there. It just in order to keep this head, it's going to transmit a lot of water. We know that. This is an experiment you can do, right? Okay. So, but there are little details to be worked out. How do we account for this little bit of porosity difference? And we'll talk about it later. Okay. But clearly, the amount of water which is going through the system is going to be a function of some sort of material property or the type of sand I'm going to pack in. If I pack clay for a given gradient, I'm going to push more water through the system. If I pack sand, other way around. If I pack sand, I'm going to push more water through the system. If I pack clay, I'm going to push less water to the system. Okay. So the overwhelming take-home message here is porosity is not going to dictate how much water is going through the system. Okay, so let's go back and now decide. So what does it dictate? Why is how do I know? So how do I differentiate clay from sand from a quantitative point of view? And this was actually let me put some. I'm going to put some. See this thing. I got a better pictures here, so maybe I should shift to this. So go ahead and take this picture. Okay. The question we just asked was a question which actually bothered the guy called Henry Darcy. Okay. And it bothered him in 18. He was actually born in. Darcy is a French guy. That's terrible. Why is it doing that? So let's draw that picture. Now a little bit about Darcy. Henry Darcy is actually one of the first civil engineers. Okay, and he talked about water supply. He's not a mathematician as opposed to other people who have contributed to this field. He really came completely from an applied point of view, okay? And he was worried about pathogens affecting Paris waters, essentially. No, Dijon waters. Dijon is a small city in France. So he's the first guy who pioneered sand filters, which you would probably see it in your environmental classes, design of sand filters and everything. So he said, well, I can use some sand to filter pathogens, okay? So his question is exactly the same question. How do I know how much flow I will be filtering if I used sand A as opposed to sand B? Okay. So he wanted to design these sand filters, which means the filtration rate of these sand beds. And so it bothered him. How do I do that? Okay. So what Darcy did was it was a very simple experiment. So he actually set up a column like this. And actually, I think he put it in a vertical direction. I have the original pictures, but it doesn't matter. We already convinced ourselves. So let's put some coordinates. So you got h. This is basically from. This is my z equal to 0. If I assume this as z equal to 0, in this case, I think I'm actually assuming this as my datum. The center of the column as my datum. Okay. So my z equal to 0 is here. Make sure you write it there. Okay. 0 is right there. Okay. So he forced head 1 here, HA, head 2 here, HB. Make this as capital H. That's a poor notation I used here. Let's make it capital H. Just to stick to. I might eventually interchangeably use big H and small h, but let's stick to capital H. Okay, and what he did was he kind of measured basically. He would force this gradient, and then he come here and have a little beaker, and simply measured how much water is coming through the system. I don't know how he exactly measured it, but if I were Henry Darcy, I will just take a little beaker, turn on my clock, and find how much water is coming. Okay, that's my flow rate, right, at a given time. And we're going to put some coordinate system to it. So I'm going to put x equal to 0 at some point here. So my A is xa, my point B is xb. Okay, my length is xb minus xa. Okay, because you got to put some coordinate direction. Okay, so what did Henry Darcy do? So he basically the first thing he did was he said, okay, I'm going to pack this column with a particular sand, okay, and then I'm going to change this gradient. So he ran the experiment for different gradients. What do you think would have happened if he changed the gradient delta H? It's the same column. He kept on changing the delta H. Would the flow rate would have gone up or gone down? Stephen.
How much you changed it?
Well, he increased the gradient, so which means he kept reducing HB. So let's say he kept HA as constant and kept reducing HB. So the gradient delta H kept increasing. Okay, what would have happened to the flow rate? Intuitively, gone up, right? So he kept doing that, and then he found HQ is proportional to delta H. Okay, and there's a negative delta H because it's a sloping gradient. Okay, so so you can put a negative sign there. Okay, because always the flow goes from higher head to the lower head. So if you work in this coordinate system, it will be HB minus HA. HB will always be lower, so it will be negative delta H. Okay. But it's a magnitude which eventually matters. It will be directly proportional to delta H. Okay, and then what he did was, the second thing is, he increased the column. He forced the same delta H, and then he said a bigger column and a smaller column. So he kept changing the L for a given. Everything else remained fixed. What would have happened, Thomas? Would Q be directly proportional to L or inversely proportional to L if you keep changing the column length? Amanda. You want to guess what happens to the delta L? Inversely proportional. Anybody else? Of course it is, because if I have a very long column, I have the same gradient, then it has to experience a lot of sand. So which means you can't push enough flow. Okay. So he found it's inversely proportional to delta L. I mean delta X or L. Okay. It's all intuitive actually. We can actually now do this kind of using thought experiment. Okay. The next thing he did was he played with the area of the column. He had a big column and a small column. What do you think would have happened? Directly proportional or indirectly? I mean, inversely proportional. Inversely proportional. If you increase area, the flow will go up or go down. Down? For a given everything else remaining same. It has to be up, right? Because everything is remaining same. If I had a big pot, okay, and I want to maintain the same level of head, I got to put ton of water because it's going to transmit a lot more water to the system. Okay, so he found Q is directly proportional to A. As I increased A, the flow rate increased. Okay, now based on these empirical observations, they are experimental observations. He formulated. So these are all proportional. So he said, okay, if that's the case, then Q should be proportional to A, proportional to delta H. Use big H everywhere. Don't use the small h. Okay, and inversely proportional to L. And then he said, okay, if that is the case, if they are all proportional, I can build this formula, and then say if something is proportional to something, then I can say it's equal to some constant times something, right? So he slapped on a constant called K. Okay, so and the yeah, I'll tell you in a minute where the negative sign comes from. Okay. So he said, well, so the Q must be equal to. So this is all exactly the same. Q is actually proportional to A, proportional to delta H, inversely proportional to L. Okay, and this is a proportionality constant. Okay, and he slapped on the negative sign because the flow goes from higher head to lower head. And I'll tell you in a minute when we do problems, we'll say why we do this. Okay. Okay, and then instead of using HA minus XP or X minus XA, he simply called it delta H and delta X, and then that can be in a continuum physics. You can turn that into a dH by dx. Okay, again, let's keep using big H. So that's the basic law he came up with, and that's called the Darcys Law. Okay. Now why do we need a negative sign? Because flow is a positive quantity. If the flow is actually going along the x direction, anything moving along this direction, the positive x direction should be a positive quantity. And if you put the numbers, it will all work out, because unless you have a negative here, because you're going to calculate delta H by HP minus HA, second minus first, and HB will always be a smaller number, and HA will be a bigger number. So when you subtract, that will be a negative number, and that negative will cancel, and you will get a positive flow rate, okay, which is actually moving towards. So when we put it in the vector form, everything will work out much better, actually. We will do that in a minute, okay? But the idea is to show that there are two types of flow. If the flow is positive, means it's going along the x direction. Now, if I flipped everything around, if I made this head higher, okay, then the flow will go this way. So negative flow means it's actually going this direction. Positive flow means it's going along the positive x direction, because by definition, I defined this is my x direction, okay? And so, because the whole thing is a vector, actually, eventually it will be a 3D problem. So we need to know the direction correct. So that's why the negative sign is there, okay? So that's called Darcys Law. That is the basic Darcys Law, okay? Now, after doing that simple experiment, Darcy kind of went on and said, well, the proportionality constant K, does anybody know what is it called? What is K? Have anybody seen it before? Come on. Richard. What is K?
I've seen it before. I don't know what it is though.
Have you taken geotech? What is K? I'm going to tell Elton. What is a major soil property? Hydraulic conductivity, okay, which is related to permeability and all that, okay. So K is known as hydraulic conductivity, okay. Now, remember, I never changed the material property here. I still packed my system with sand, okay. So we are still dealing with sand, okay. So that's what Darcy initially did, okay. So that K is a property of the material. Okay, if I fix the material, it's going to define a number, okay, and for sand it's defined. Okay? But if I changed clay, it's going to be a different number. The whole thing is off. It will be different type of flows, but the relationships will still hold. It will still be proportional to L, inversely proportional to L, directly proportional to delta H, and so on and so forth. But the property, the constant will be different, okay. So Darcy later on went on and did even more experiments, okay. So he said, okay, what if I repeated my experiment with different diameters, different type of soils, basically. Oh. So he packed the system with different type of soils and found terrible. Okay. Well, I'll use the blackboard. That's not working. You don't like this. Okay, so he repeated the experiments and found Q is directly proportional to square of the diameter. Okay? Particle. Nice, okay. And he also found Q is directly proportional to the density of the fluid. He ran it with different fluid. Actually, he did not do all these experiments. Later on, people found that, actually, found about it. Okay. Darcy did very simple experiments with sand columns. Okay. Q is directly proportional to rho g. Okay. And then if you change the viscosity of the fluid, you will find Q is inversely proportional to viscosity. Okay. Now, note rho is equal to, specific weight is gamma is equal to rho g. Okay, so this is actually gamma. Okay. So with this information, I can write so-called expanded version of the Darcys law. So now law becomes Q is proportional to d squared rho g a mu delta h and delta x, right? So all these experimental observations can be slapped in. And now I can throw another proportionality constant, and I'm going to call that as C. Okay? And the C is known as shape factor. Okay? And it is dimensionless. Okay. Now, typically, people do not just find C. Instead, they club C and D together and define another constant. So they would just combine C and D squared together and create another constant called Ki. Okay. So define, this is purely a definition from tradition. Ki is C times D squared. Okay. And Ki is known as intrinsic permeability. Or basically it's also called soil permeability. Okay. It's called intrinsic permeability because it's purely a function of the material property. It's just a function of some constant, some corrective factor times d squared. Okay. So which tells that intrinsic permeability is purely a function of the diameter of the particle. Okay. So now let me go back and remember the very first lecture we talked about packing a box with tennis balls and then bigger beads and smaller beads. Okay. So now if I changed, if I did the same box experiment packed with big balls as opposed to small glass beads, which one will have a higher permeability or higher conductivity? Small bead or a big bead? Big bead has a higher conductivity? Okay. Thomas. From a conductivity, hydraulic conductivity point of view, we proved ourselves that it's not a function of porosity, it's the same. Now, if I packed a column with big beads and small beads, which one will have a higher conductivity and why?
The larger particle size
Will have a higher conductivity?
based on d squared.
That's right. This tells me it has to be a function of diameter, and as I increase my diameter, the hydraulic conductivity is going to go up because, well, actually I have not defined hydraulic conductivity yet. So let me go ahead and define. So that's my intrinsic permeability, and I think this is what you guys use in geotech actually, permeability. It's in Darcy and all that stuff, right? But most of the time in groundwater, we're dealing with groundwater problems. So we're going to lump all this together into hydraulic conductivity, and I'll define that in a minute. So let's put Ki here. So if I put Ki there, then I can write Q is equal to minus Ki rho g a mu. Well, there is always a negative sign. Keep that in mind, just to keep the directions right. Delta H divided by delta X. Okay. And this whole thing is what is K. Okay. So now, I mean, initially we defined Darcy's law like this, right? K minus K times A delta H by delta X. So A delta H by delta X still stands. Oh, sorry. Okay, so that was the original Darcy's law. By looking at different properties, we can expand K. So K is defined as Ki rho G divided by mu. Okay. So K is defined known as K is hydraulic conductivity. Okay. Ki is intrinsic permeability. This is purely a function of material. Okay. Whereas this is a function of fluid and material. They are added together. Okay. And in terms of units, what is the unit of Ki or dimension of Ki?
The particle size.
What would be the unit? Typical unit of Ki will be millimeter.
I mean, particle size.
Yeah, but what should be the unit? Is it in Newton, joules, centimeter, millimeter, or length unit, or what do you think the dimensions of it should be, Thomas? From here, you should be able to say that. It should be length squared, right? Dimensionally, it should be length squared. So it should be millimeter squared or centimeter squared. Whereas the hydraulic conductivity, if you put all these units, you can convince yourself it will be length squared by time. So typical units will be meter squared per day, okay, or centimeter per second, something like that. Oh, sorry, length per time. Length per time, that's right. Okay, that's the length per time. Now you can work it out actually. If you put the rho, g, and mu proper units, you will convince yourself it will be length per time. This will be length squared, so it will be like centimeter squared or meter squared. And it's also called this Darcy, which I never use. I think the geotech literature uses this Darcy, which has got some weird definition. So I'm going to stay away from that unit, okay? So or feet, whatever you can use. Any length, and this is length per time. Okay. Now, what were we talking about? Okay, about to say something, I forgot. Okay. So anyway, so the hydraulic conductivity is a property which is a function of the fluid property as well as the intrinsic property of the porous media. Okay. So now let's think about it. So if I did my box experiment, I said, if I fill the box with the big spheres as opposed to small spheres, the porosity remains same. So remember, all these arguments, porosity never came up, right? Okay. Now, so if I did a column experiment filled with big spheres as opposed to small spheres, which one will have a high conductivity? Big sphere will have a high conductivity. Based on this argument, why? Fang. What do you think? Would big sphere have a high conductivity or a small conductivity? So I'm going to take a little column, fill it with glass balls. Okay, one with big balls, the second one with small beads. Okay. Will be smaller. Okay, that's good. Okay, so now we're getting into interesting territory here. I like that. Large, small spheres. So these are small spheres, large spheres. Okay. So conductivity will be. The question is, conductivity will be. Which one will be large? You think this one will be larger?
No.
K will be large here. Higher. Which one will be higher?
Larger.
Here? Okay. Anybody else?
It's small.
Small? Okay, great. I got 2. Okay. Okay, so so let me get it straight. So if I had a smaller glass bead, it will have a higher conductivity.
You have more smaller beads than the large beads, right?
That's right. Of course,
You're filling it.
that's right. You will be filling in. So it'll have more conductivity. Can you explain why? What do you think that way?
Because you're squaring the area of the small beads and taking the sum of them.
Ah.
I'm trying to explain what I'm thinking.
So the Ki is
Squaring the sum of a bunch of squares to the sum of.
but K that becomes smaller though. D becomes smaller. Remember that. Okay. The diameter itself will become smaller. So you're squaring a smaller number.
But you have a lot more of them.
Yeah, a few more of them. Okay, but I see your point actually, but
That only matters for a single particle.
not necessarily. You're filling this whole column with these beads, right?
Yeah, but when you calculate Ki, it's just you're taking the average particle size.
That's right. Yeah, that's right. Yeah, that is the point actually. So when you're calculating Ki, you're actually taking the average particle size, not a characteristic particle size. Okay, and but I see where you got confused actually. But the point is, well, let's think about the other way around. Okay, which would decide what is the reason for the conductivity being higher or lower, which is all related to flow rate, right? Eventually it's related to the flow rate. We're forcing a gradient, and as I change my conductivity, the flow is going to become less or small. Okay, why is the flow rate going down, for example? Okay, but if I had a very permeable system, the flow is higher, right? A pot filled with sand, the flow is higher. A pot filled with clay, the flow becomes smaller for the same gradient. Why is it? What's happening in the system?
There's a whole lot more pores that there's forces acting on.
There is no, don't get into the pore discussion because that's a big trap, okay? And so what happens? What do you think it's got difficult to conduct?
There's more force.
More friction. That's right. There are losses. Just like your energy grade line, when you draw in pipe, there is more friction loss. The flow is going to go down. So obviously, clay is somehow producing more losses. Why is it? Why would clay produce more loss? Which one will offer more surface to interact? The roughness will be proportional to surface, right? So as I go smaller and smaller bead, I got more and more surface, right? Which means the fluid is going to rub against a lot more surfaces, which means it's going to lose a lot more energy. Okay. That's the reason everything goes down. Okay, so you're right. We are filling more particles, but just think about it. If I had a column with one big bead, there's a very little surface. If I broke that little bead into a lot of tiny beads, I created an enormous amount of surface. And the fluid has to now navigate through all these surfaces and rub against them, so it's going to lose a lot of energy because of the friction loss, essentially. What do you think happens to the friction loss? That energy, where does it go? That loss of energy? Heat, actually. It's a tiny, tiny heat, actually. If you calculate thermodynamically, it'll be like 0.000001, this thing. But everywhere, when things lose your friction factor in the pipe flow or anywhere else, or porous media, when you do a geotech experiment with a little column, you actually generate some little bit of heat energy. It's tiny, 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 tiny energy, but you do generate some heat energy. That's how it's lost. Okay, so that's why when I go with smaller beads, the K will actually become smaller because there is more friction to deal with, more conductivity. Okay, whereas if I have a bigger bead, it's going to be a lot faster, basically. Okay, so this is going to decide how fast or slow the porous media is going to transmit water through the system. Okay, so let's kind of look at some numbers. Oops, I don't have time. I'm gonna rush now. Okay. So K is a constant. So in summary, so the Darcys law is Q is equal to minus K A delta H by delta X. Okay? Where K is the hydraulic conductivity, okay? The unit is length per time, okay? Or meter per day. Okay. Now, similar to and delta H by delta X is known as hydraulic gradient. What's the dimension of this, delta H by delta X? Hydraulic gradient. Dimensionless, thank you. Length by length, so it's dimensionless. Okay? So this is dimensionless. You can actually derive the conductivity here. Q is cubic meter per day, must be equal to meter squared and dimensionless, which means this has to be meter per day. Right? So you want to always check those units. Okay? So now you need to have some feel for these numbers. So K is a function of property of the soil. For a typical sand, coarse sand, or beach sand, 100 to 1,000 meter per day. Okay. Fine sand. Okay, actually, this is not a beach sand. It's coarse. It'll be really coarse, like a construction sand. This is the beach sand. Okay, you might want to keep one unit because then that way you can soak in some numbers. Okay, and I prefer meter per day. Okay, so if I remember this, then I can convert feet per day or whatever I want. So that's kind of a rough estimate. Silty sand. Clay. So these are some rough estimates, okay? And now, and these are usually experimentally evaluated property, okay? If you want to compute the value of sand, you can look at tables, but in the end, you really need to do some experiments, okay? That's the only way to compute the value of the hydraulic conductivity. Okay? Now, based on what we learned so far, let's say I took you to Orange Beach and we sampled some sand, and I said, find the hydraulic conductivity. What would you do, Megan? I would say, like, you took groundwater class, he harped about hydraulic conductivity for a whole hour. Find that.
I guess I'd do grain size distribution.
That's one way to do it, but I want use this lecture to do it. Actually, the sand we have in the lab, if you want to find the hydraulic conductivity, what would you do?
Find the flow rate through it.
Okay, so I will give you a column. You should first ask me, give me a column. I'll give you a column. And you should ask me, give me a couple of manometers, right? So I would set up this experiment. I would essentially set up this experiment and put a little pump there, okay? And I pump some flow to the system, okay? And I'll attach a manometer. Okay? And the manometer will show a certain delta H. Okay? So I will measure Q versus delta H. Okay? And I'll pump Q equal to some number, say 1, and I'll record my delta H. I'll double the flow rate, 2. Record the delta H. Okay? And this equation can be now plotted because I know the area of the column. I will measure it, right? I know area is known. So if I now plot Q versus, and delta L is also known, right? So I can go back to the Darcys law. Q is equal to minus H A delta H by delta L. I know delta H, which will be, assuming you push this way, it will be a negative number, right? So the negative will cancel. Then I can plot it. Slope will give me the conductivity. Right? That's how I measure it. Okay. Now, from the grain size, what he said was you'll estimate it. Okay, that'll give me some rough approximation, but that's the measurement. That's how I'll measure it. Okay? So, and these are usually based on such measurements. The hydraulic conductivities lie along this range. Okay? So let's do a quick, let's say Dr. Lang asked Megan to actually set up a column, and she actually did this and found HA equal to 2 meter. Her area of the column was 5 meters squared. HB equal to 1 meter. L is equal to 2 meters. She went to the lab, did all this. 5 meters squared, L is 2 meter. And she was pumping flow rate of 1.25 cubic meter per day. Just one experiment. She said, oh, she's just kind of lazy. She said, I'm going to just do one experiment. Okay? And then she brought it to the class and said, I have no clue what the hell is going on. This is what Dr. Lang asked me to do. You guys tell me what's the K. How do we do that? That's the data she collected. But she did hard work. She collected all this data. You got to give it to her, right? So how do we do this? Can you go ahead and do it, actually? Let's find K. So anytime, I can't ask Megan for this. So Arthur, how do we help her out?
And you know the equation for Darcys Law.
Okay, which is minus Q minus K A HB minus HA divided by L. Okay?
And you know everything.
Everything is known, so let's put the number. So K must be equal to Q divided by A HB minus HA divided by L. Okay. So all we need to do is some little bit of algebra. So Q is given 1.25, A is 5, HA minus HB is what? No, sorry, it's HP minus HA. HB minus H. HB is 1 minus 2 divided by length. What is length? 2. And there is a negative sign, so there has to be a negative sign. And the negative sign will cancel here. Do you see that, how it works out? So what's the number? Can somebody quickly calculate that for me? How much? 0.5 meter per day. Okay. Now, she just wanted to confuse you guys, and she said, well, I'm going to do another experiment. Okay. She did another experiment. Everything was the same. So it's the same column, A equal to 5 meters squared. Length is equal to 2 meter. And she even pushed the same flow. But she said, well, my HA is 1 meter, HB is equal to 2 meter. What is my K? 0.25? What do you think she did actually?
Opposite direction. I don't know, the side of the column.
She did nothing. She just took the pump and put it on the other side. She reversed the flow direction. That's all it is. Okay? And if you look at the negative sign, that's why the signs are very important. So she should be actually reporting this flow as a negative flow because she flipped it around. Okay? The flow direction has got some meaning to it. That's my point here. Okay? So where you keep the pump, the equations kind of work out eventually. Okay? So that kind of concludes my lecture on Darcys Law. So that's kind of the basics of Darcys Law. And you might want to start looking into homework number 2, because homework 1, by this time, you should have a pretty good hold on it. So you might want to start looking at the homework 2, where we have some example problems on how to use Darcys Law to calculate some conductivity values, flow values, and so on and